This is Neha Sinha presenting an extra credit video on the Higgs boson and the CERN program, which is a European organization for nuclear research. The lecture I attended was entitled A Discovery, the Higgs, Why is it Important, How it was Done, given by Howard A. Gordon of the Atlas collaboration. So the announcement that the Higgs particle was discovered was made this past year on July 4, 2012. Now, in truth, the Large Hadron Collider, or the LHC of the CERN program, simply discovered a particle of about 126 giga-electrovolt mass, which was the estimated mass of the Higgs boson. So they're pretty sure it is the Higgs boson. Several additional experiments will need to be conducted to discover more and to confirm this discovery scientifically. So I want to explain what I've learned from the lecture about the Higgs and what I've learned from external sources about the LHC. The idea behind the Higgs is that there exists a field similar to an electric or a magnetic field called the Higgs field. As particles such as protons and electrons travel through this field, they gain mass. The analogy Gordon provided was a celebrity walking into a crowded room. Here, the celebrity represents a particle and the people in the room represents the Higgs field. As the celebrity walks through the room, people, or the field, surround the celebrity or the particle and give the particle mass. A direct result of the Higgs field is the Higgs boson, a particle that, if found to exist, will complete the standard model of particle physics. Now, this is the particle thought to have been discovered last July. But why is the Higgs field important? Well, first, it fills in holes in our knowledge of the weak force. And second, it explains why particles such as electrons have mass. The mass of an electron, or the electron cloud, determines the radius of an atom, and atoms make up all life, so therefore life would not exist without the Higgs. So the Higgs boson is one of the many things that the CERN program and Atlas are specifically trying to find. Now that they have discovered the particle, many years will be spent trying to identify its properties. And I'm incredibly interested in this because it's just amazing to think about the fact that there's a completely other field that permeates the universe and exists around us, through which only the smallest of particles can travel. So now we've talked about one of the things the Large Hadron Collider is trying to discover, but we haven't really talked about what the LHC is. And it's an incredibly interesting collaboration project of over 60 nations. It consists of 27 kilometers of underground tunnel through which protons are sent at incredibly high speeds to collide. And these collisions are analyzed by detectors along the tunnel, as seen here. Now this animation shows the protons traveling through the tunnels to collide within a detector. Here's the collision. After attending the lecture, I was really interested in learning more about what the LHC is intended for. And in researching this, I found a rap describing the components of the LHC and each of their purposes. And I've put the link to this in the description, and I highly recommend watching it because it's both entertaining and highly informative. The rap delves into dark matter and antimatter, two other elements of the universe the LHC attempts to experiment on and learn about. As Gordon talks about in his lecture, visible matter takes up only about 5% of the universe. 25% is dark matter and 70% is dark energy. Now, dark here simply refers to the fact that it cannot be seen. Instead, dark matter is identified by the way it interacts with the rest of the universe. Dark matter essentially holds the universe together. In addition to dark matter, there's antimatter. I looked at the difference and found that dark matter and antimatter are strongly believed to be different things. This creates a question CERN addresses on what dark matter is composed of. One theory is that dark matter is just too dim for us to see. And another theory is that it's an entirely different type of matter called baryonic matter. Now, antimatter should theoretically exist in the same quantity as matter, visible matter, that we see, but we have not yet discovered large quantities of it anywhere in the universe. Antimatter, according to the rap, is like matter's evil twin because a particle and its antiparticle are the same in every way, including mass, except for spin and charge. They have exactly the opposite charge. When matter encounters antimatter, both annihilate. In the LHC, they create matter from energy and collisions, which appears as both matter and antimatter in equal parts. This is accomplished in the LHCb section of the LHC. So hopefully you've gained some insight into what the Higgs is, as learned from Howard Gordon's lecture, as well as what the LHC is intended to accomplish. Thank you so much for watching.